be about neutron stars. And you may be wondering why I, of all people, will be introducing the speaker about neutron stars. And this is because today is a talk about unity of physics, I would say. It's neutron stars, but you will learn that in neutron stars there is something directly related to softness. Surprisingly, you touch the star and apparently it's soft. So this is what we will learn today. Our speaker is Chuck Horowitz. He comes to us from Indiana University in Bloomington. I think Chuck defended his PhD in 80s in Stanford, if I get it right. It turned out that I heard him speaking about something entirely different in Aspen, but then I forgot about it, and I read his wonderful review article in Reviews on Modern Physics, and that's how I got to know him. And Chuck, please tell us about unity of physics.
So thanks very much, and thanks for the chance to come. I really appreciate it. The chance to talk to the students this afternoon. And please interrupt as we go along. The less I get covered, the better. Let's see. Whoops. Okay. I chose to define astromaterial science, study of material and astrophysical objects that are qualitatively denser than terrestrial materials. So I'm thinking maybe compact objects like dwarfs or neutron stars, where you have material that's much denser. Okay, and this is both new and not new. The dense materials may have unique properties, such as great strength. So we believe we've found the strongest known material, but I'll get to that. But they may be organized like terrestrial materials. So the first is saying density is new, and the other is matter is matter, and condensed matter in astrophysics is similar to condensed matter in some other field. Okay, so in the talk, I'll just give you one example of a hard astromaterial, and I'll talk about plasma crystals. So these are solids in cold white dwarfs and the crust of neutron stars. Okay, so that's a crystal, and then I'll also talk about nuclear pasta, the most favorite, personally, phases of matter in a neutron star, and I'll say this material has something in common with soft terrestrial materials. Great. Whoops, I'm learning. Okay, step one, throw out all the chemistry you learned in high school and the periodic table. At high density in a white dwarf or a neutron star, atoms are pressure ionized. All the electrons form degenerate relativistic Fermi gas. Don't worry about the relativistic bits, but the electrons are gone. So there's no electrons, no closed electronic shells, no periodic properties.
By gone, you mean uniform, of course.
That's right. They're gone into the degenerate Fermi gas, and the Fermi energy of the electron gas is higher than any other energy in the problem. So the electrons are essentially unperturbed. Okay, so you have nuclei that form a Coulomb plasma, and those ions could possibly form a Coulomb lattice, Wigner solid, the melting temperature of the lattice, so just set some thermal energy equal to some Coulomb energy, z squared over r. R is a typical distance between ions, and if you got a fixed electron density from the electron gas, then the distance between ions scales like the atomic number to the 1/3. So you have z squared over z to the 1/3. The melting temperature scales as z to the 5/3. So if you'd like, here's all of chemistry, in at least my chemistry, in one line. Okay? So instead of a periodic table, and it's just a smooth dependence on z.
In NYU context, it would be good if organic chemistry would be also hidden in this one.
Can we not go this way?
Okay. No organic chemistry on neutron stars for this. Okay.
Question over here. What's the reason for the 175 in the melting temperature?
So the one component plasma, there's history to a system of just ions with a uniform neutral background. And the melting temperature is actually the Coulomb energy divided by 175 is kT. And that's some relatively early Monte Carlo simulations determine that 175. Okay, think of the ions. They have z squared over r Coulomb interactions. The electron gas is slightly polarizable, so I'll include a screening length. I don't follow the electrons explicitly. They're slightly polarizable, so there's this screening length, lambda. Lambda is relatively big, so the screening is a pretty small correction. We include it because it makes the molecular dynamics simulations easier. Okay, so we have simple molecular dynamics simulations in the ion coordinates. And so basically the whole talk is just some simple MD simulations. Let me start by asking, how does the Coulomb plasma of ions in the core of a white dwarf crystallize? Okay, how does a star freeze? Let's see. 2 seconds, if I may. I guess there are people online. Should I point with the mouse pointer or with the pointer at the screen? Maybe I'll do this for the online. Watching stars freeze is a lot like watching paint dry, only a lot slower. So NGC 6397, this is a star cluster, a nice, pretty Hubble image. Didn't get it all. Counted the number of white dwarfs in the star cluster with different luminosities. Okay, a white dwarf is the mass of the sun, the size of the Earth. It's born relatively hot. There are only a few nuclear reactions, so it just cools with time. Okay, so it starts hot, which is a small luminosity, a small numerical magnitude, and then it cools off. So stars move to the right with time. Okay, but the cooling rate is not uniform. When a star starts to freeze, there's a large latent heat. Okay, so it's just like the ice cubes in your iced tea that keep the tea near freezing temperature. So for a while, the star is radiating away energy and getting colder. Then the star is radiating latent heat away and staying the same, staying the melting temperature. Okay, so it actually, there's a delay in cooling just from the latent heat. And that leads, I said I was going to do this. This peak here, we believe, is due to the latent heat. You see extra stars with that luminosity because when white dwarfs have that luminosity, they're freezing, and it takes them longer to freeze. Okay, Vinget et al. Had a theoretical prediction, which is the red line, and it agreed very well with observation, and that confused him. The reason he was confused is because the red line was for pure carbon. He was thinking white dwarfs are about a 50-50 mixture of carbon and oxygen. I told you Z to the 5/3. So 8 to the 5/3 for the oxygen is 60% higher than carbon. Okay, so pure oxygen melts at a 60% higher temperature. We think the star is about a 50-50 mixture, and he observes that it's freezing around the temperature of carbon. Okay, and the answer is the phase diagram. So this is our molecular dynamics simulation. Let me start over here. Put about 50,000 ions in a box. We actually, the initial conditions had half of it solid and half of it liquid. Adjust the temperature carefully so it stays about 50-50, and then actually run it at constant energy, and the latent heat drives the system to the melting temperature. So after it equilibrates, we read off the temperature. So this blue square and red square, the temperature for that simulation was about 25% more than the temperature of pure carbon. Okay? Then we count the number of carbon and oxygen in the center of this crystal, determine the composition of the liquid. The solid is actually oxygen rich, and the liquid is a little bit carbon rich. We started with a 75% carbon and oxygen, and it goes to 80% oxygen in the solid and 70% in the liquid. Okay? And in particular, this 50-50 point, or this point near 50%, is the one that's relevant. We think a white dwarf many white dwarfs are about 50% carbon and 50% oxygen. And the melting temperature here is actually very close to the melting temperature of pure carbon. So this is the melting temperature in units of pure carbon. There's carbon and there's oxygen, 60%. Okay?
Is it uniform through the volume, the composition?
So the composition is pretty uniform. We can actually map out the gradient across the interface, but the simulation was big enough that exactly where in the solid we take the composition doesn't matter so much.
No, but in the actual star, when you have
I'm sorry. This freezing actually transports oxygen towards the center and pushes carbon out further away in the star. So as the star freezes in the center first, and then as more and more the star crystallizes, the crystallized part is oxygen rich, and the outer part is carbon rich. So you actually do move the composition.
So there is some non-trivial dynamics at the front, huh?
Yes, you're actually diffusing carbon outward.
Why a small concentration of oxygen temperature, melting temperature, is even below pure carbon?
Impurities weaken the solid. So if you put a few impurities, it doesn't matter that they happen to be oxygen. Then the impure solid is a little easier to melt than the pure solid. Okay, great. So that's freezing in a white dwarf. That was a warm-up problem. Now I really want to talk about neutron stars and their crust and get to nuclear pasta. Okay, so neutron star is formed in the collapse of a massive star in a supernova. You've got the mass, half again the mass of the sun, radius about 10 or 12 kilometers. We think that a neutron star has a solid crust about a kilometer thick. So think of an eggshell over a liquid interior. So nuclear matter is a quantum liquid. It's the 0-point motion of the protons and neutrons that keep it a liquid even at 0 temperature. So we think the interior of the star is liquid. The exterior of the star is a Coulomb solid, exactly like a frozen whiteboard. So a degenerate relativistic electron gas, you have ions. There's one new twist. As you go deeper into the star, the high Fermi energy of the electrons actually drives electron capture. And so the nuclei become more and more neutron rich. And at a density about 10 to the 11 grams per cubic centimeter, the neutrons actually drip out. So in this inner crust, you have an electron gas, you have the ions, and then there's also a neutron gas. Okay, and then finally, the nuclei, as you approach nuclear density, the nuclei in the crystal lattice get closer and closer together. And when they start to touch, wild things happen. And that's these complicated nuclear pasta phases. So the nuclear pasta, there's about 100 meters at the bottom of the crust where you have all these different shapes, and I'll get to that. And the nuclear pasta is the interface between a crystal lattice on the outside and uniform nuclear liquid in the interior. Okay, great.
And so the only role of gravity is to maintain the Fermi gas in its degenerate state, but it also seems to be providing some sort of orientation.
So gradients are not so important. The most important thing is simply the weight of all the material above you sets the pressure. So as you go deeper in the star, the pressure's rising.
But gradients aren't important.
So across a small sample of the condensed matter, the gradient is small.
So a naive question, is this all theory or there is?
It's not a naive question, it's a real question. It's the right question.
No, I mean the structure of the neutron star. Is there any experimental evidence and how you get it? And
Yeah,
for example,
so that's
what types of
exactly what
crystal-
I wanted to do. So thank you. I didn't plant that question, but it's perfect. Are there any observations? And the observations that neutron stars really have crusts come by observing how fast the surface of a neutron star can cool. Okay, so there are systems, low mass X-ray binaries, conventional star and a neutron star. A material accretes onto the neutron star. And so the great gravitational binding energy of the neutron star, when the material hits it, it gets very hot. Okay, so this is, the all-sky monitor is a large field of view X-ray instrument on the satellite RXTE. This is time and days since January 1st, 1996, and this is about 10 years. Okay, so 1996 to 2006. And you see all this stuff here. So there's a lot of X-rays, materials accreting onto the neutron star. There's a lot of gravitational energy released, and it comes out as X-rays. So while it's accreting, this is all heating up the surface of the neutron star. But you can't see the surface of the neutron star because there's all this accretion. But then the accretion stops at some point. And then the rest of this is essentially background. The all-sky monitor is not a very sensitive instrument, although it has a large field of view. So you come back with a more sensitive X-ray telescope at particular epochs, such as Chandra. So at this point here, which is shortly after accretion stop, you see that the surface of the neutron star is hot. You come back 6 or 8 months later, and the neutron star has cooled. So you're watching the cooling of the neutron star in real time. And the relevant time is time since accretion stopped. So accretion was observed to stop here, and then we just look at it later and later times. Okay, and the red dots are the experimental observations. So surface temperature in million Kelvin. So 1.2 million Kelvin going to about 0.8 million Kelvin as a function of time, and you see this is a few years. Okay, so you're watching the neutron star cool. So we can't experiment on a neutron star in the lab, but nature was very kind and kicked this neutron star with accretion, and we can watch how she responds.
Could you tell what type of crystal it is, or just?
Yes. So let me get to tell you what we can tell about the crystal. So the red points are observations, and this theorist did a cardinal sin, and he doubled the 1 sigma error bars and plotted 2 sigma error bars. So these are theorist 2 sigma error bars. Never mind. So that's the data. All these curves here assume a crystalline crust that's relatively clean with a high thermal conductivity. So you have this degenerate electron gas. Because it's degenerate, the electrons have a big mean free path, and so that's a relatively high thermal conductivity. This dashed line up here, which cools much too slowly, that's for an amorphous solid. So if you had a liquid, or amorphous is essentially just like a liquid, then there's too much scattering between the electrons and the amorphous solid, so the thermal conductivity is lower, and it would take many more years for the star to cool than is observed. So these observations show that neutron stars, the surface layer of a neutron star has a high thermal conductivity, which is consistent with a relatively clean crystalline crust. And in fact, you can set limits on the purity parameters, and the crystal is relatively clean. Okay, so these are observations that we take as strong evidence that their crust is really there. Okay, so we proved there really are neutron star rocks. They're a solid material.
That length scale that you told us about, that it's about 1 kilometer thick, the
Yes.
crust, is that something you can infer from this as well?
So if you think of a cooling wave diffusing from some depth in the crust out to the surface, the deeper you are in the crust, the longer that time takes to diffuse out. So the later you observe it after accretion stopped, that's probing the thermal conductivity deeper in the crust.
Just naive question. How general you expect this structure to be? For instance, it would also work for, let's say, magnetar or other kind of.
So, let me see. Lack of evidence to the contrary. We assume the magnetar crust is similar to the crust of a low mass X-ray binary. We don't think there's so much difference between an accreting crust and equilibrium crust. They have slightly different composition, but the effective impurity parameter for the accreting crust is observed to be pretty small. So we think most neutron stars have a nice clean
just like when you treat hydrogen ion, they'll fuse further down in the.
Yes, so as you go deeper,
Yeah.
the composition, of course, is changing.
And that would release some latent heat.
So that's right. And the analysis includes some what they call shallow heating. They also include the deep heating from electron capture and piconuclear reactions in the crust. As you drive material deeper in the crust, the reactions release.
Is the crystal spin aligned?
Probably not. You have a strong magnetic field. There are some interesting things, probably relatively shallow depths in the star. But if you get deep in the star, the energies of the crystal get high compared to magnetic energies. I'm having enough trouble modeling the non-magnetic crust. I'll come back. Maybe that this is an excellent time to punt on magnetic. Instead, so I have two things I want to do. I want to use the neutron star rocks, and then I want to get to nucleoplastic. And so let me try and do that. One thing you can do with rocks is build a mountain. You can't build a mountain so well if it's liquid. Okay? So there's a mountain, and so I've drawn a giant mountain. It's not to scale. Maybe it's close to actual height. So 1 centimeter is a very, very tall mountain. And actually, what I really mean is large-scale deformation of a neutron star. I'm going to be interested in the quadrupole. So it might be 1 centimeter high and kilometers wide. I'm interested in a significant fraction of the 10-kilometer-ish radius of the star. Okay? And now if you have a rotating star, it turns out just having a weight and making it go around in a circle, that's a really efficient way of generating gravitational waves. Okay? Mountains on rotating stars, if they exist, involve large mass undergoing large accelerations, and they efficiently radiate gravitational waves. Okay? So I'm going to show you some LIGO data searching for neutron star mountains. A strong gravitational wave source places extraordinary demands on dense matter. Okay? You want to, my cell phone, when the battery is good, generates electromagnetic waves by accelerating electrons. You want gravitational waves? Well, you put a mass on a stick and you shake vigorously. Okay?
You will not emit gravitational waves if you put a mass on a stick, because H omega will be much larger than the actually emitted energy.
So
when I move my arm, I don't generate gravitational waves. Quantum.
let's leave quantum aside for a moment.
Your example is bad.
If you wait longer.
Nevertheless,
Did you try to generate gravitational wave, and that's how you damage your arm?
He was trying.
Very good. To overcome objections from the audience, and not just by cripples, we need both a large mass and a strong stick. Okay, and it turns out lots of people have thought about the strong mass, but I'm an astromaterial scientist. I want to talk about the strong stick. And it's not just how strong is this stick or that stick, but what is the strongest possible stick that you could have. Okay, and you need the stick to actually accelerate the mass. Okay. So let's take a break for just a second. I'm really excited with the opening of the gravitational wave sky. So LIGO is amazing, and this is a very exciting era. These are historic times. LIGO has seen a bunch of black hole mergers. When it's operating, you get about one a week. It's seen a few neutron star, and black hole neutron star mergers. And I'm very excited about those. But what else could be out there? What else is out there? Okay, when Galileo opened up the night sky with his telescope, he saw mountains on the moon. Could LIGO observe mountains on neutron stars? Okay, we have this whole gravitational wave sky, and we've only seen a couple objects. What else could be out there? And that's a really exciting question. Okay, how strong is my stick? How big a mountain can I hold up? So this is work done with computational material scientist Kai Kadau. At the time he was at Los Alamos. For some reason, his day job then was to do molecular dynamic simulations to determine the mechanical properties of plutonium when it's under extreme pressures. Okay? So that was what he was doing. I talked him into also simulating the breaking stress of neutron star crust, and real materials have impurities and dislocations and grain boundaries and complications like that. And here's one of Kai Kadau's simulations. There's 13 million ions, and he freezes a layer at the bottom and a layer at the top and moves them against each other to strain the sample. So we want to figure out how strong the crust is. If you do this, for example, here's silicon, a conventional material in the lab, and a void opens up. You fracture the material, and you pull the layers of ions, or atoms in this case, apart like a zipper. So a conventional material fractures, but in a star, there's this huge pressure holding everything together. You can't have a void in a star because of the strong pressure. So as you, so let's see, yeah. So he's moving this frozen layer here at the top, and the red is deformations of the crystal lattice. And it starts to deform along the grain boundaries, but the high pressure keeps it all together. It never fractures, and it does eventually fail, but it only fails after you've strained it a large amount. So the bottom line is we find neutron star crust because of this high pressure to be incredibly strong. So if you like, we find neutron star crust is the strongest material known. It's 10 billion times stronger than steel, which is a pretty useless number.
But if you do pure shear, it does not involve volume change, and therefore pressure would not.
That's right, but as you're shearing it, the volumes don't open up. If you shear silicon, even though you're not changing the volume, you will fracture.
You will, yes.
Yes. But because the material is under high pressure, even though you're not changing the volume, you can't open a void.
So is the 1 centimeter then, is that the balance of the yield stress of this material against the surface tension?
So the neutron star gravity is incredibly strong. And so basically it's the elastic force compared to the gravitational force.
And you're saying that the surface tension doesn't matter? It's going to be pretty impressive because it's going to be like on the scale of the Fermi energy.
You have 10-kilometer mountain. So you're not changing the surface. the curvature is really small. Okay. John, this is a busy slide. What I did want to do is just say these blue dots are data. So these are LIGO observations, and I wanted to show you some data. I'll explain that in just a second. The maximum possible mountain depends on the strength of the crust. Our crust can support ellipticities of a few 10 to the minus 6. Ellipticity is the fractional difference in moment of inertia. If you rotate the star around the third axis, if the two equatorial moments of inertia are different, then as you rotate the star, that's a time-dependent quantity. So that generates gravitational waves. Okay, this is a small number because you only have this thin eggshell. You only have a kilometer solid at the top, and the gravity is really strong. And of course, the gravity wants to keep things round. Okay. H naught is the gravitational wave strain. So that's delta L over L, this 4-kilometer LIGO interferometer. Okay? These are crazy small gravitational wave strains. 10 to the minus 25 or 10 to the minus 26. The first observation had a strain of 10 to the minus 21. So these are changes in length that are 10 to the 5th times smaller than when you collided two big black holes. Okay? So what LIGO does is search for gravitational waves at twice the frequency of a known, twice the rotational frequency of a known pulsar. Okay, and so you can carefully search for each dot is a known pulsar, and they don't observe any continuous gravitational waves. They set an upper limit on this. G over c to the 4th is this miserably small coefficient for gravitational waves. The moment of inertia of a neutron star is largely known. The frequency is twice the rotational frequency. D is the distance to the star. And so you can directly set limits on the shape, the ellipticity. And so these stars rotating at higher frequencies have ellipticity limits smaller than the maximum ellipticity the crust can support. So LIGO is directly measuring and setting limits on the shape of these neutron stars. We haven't seen anything yet, but we keep searching, and we're proving neutron stars are very round objects. Oh gosh. So in the last 2 hours of my talk, I did want to talk about nuclear blast. Great.
But this wouldn't test if they're oblate spheroids, like,
That's right. So the Earth has an equatorial bulge where both I1 and I2 are different from I3, but I1 equals I2. Okay, nuclear density is about 310 to the 14 grams per cubic centimeter. It's the density inside a nucleus. Nuclear matter wants to have that density. As you approach nuclear matter density, there's a complex competition between short-range nuclear attraction and long-range Coulomb repulsion. So this is Coulomb frustration. Because of the nuclear attraction, nucleons want to be correlated at short distances and anti-correlated at large distances because of the Coulomb repulsion. And how can you be correlated and anti-correlated at the same time? You get frustrated. So that's Coulomb frustration, and that's how the world is organized. Okay. And you can get all these wild shapes, and I'll show you those.
Sorry, Chuck, can you repeat this thing? So if I distribute the nuclei at uniformly, then they will in fact repel. And when
So-
they touch, they will attract, correct?
Yes. And now let's go to the nucleon coordinates. So let's distribute nucleons because they don't stay nice spherical nuclei. And so let me just make a simple semi-classical model. We have a short-range nuclear force. There's an intermediate range attraction, a short-range repulsion, and we adjust those parameters so that nuclear matter saturates, so it likes to have nuclear density, and it has the right binding energy. Okay? So these terms would cause the nuclear matter to want to be a uniform slab at nuclear density. And then, of course, we have Coulomb repulsion between the protons. And we actually include the electron screening. I didn't.
So you mean Bij are next?
Oh, I'm sorry. The Ij is whether you're a neutron or a proton. So we have slightly more attraction between protons and neutrons. There's a bigger attraction between a proton and a neutron than between two protons.
But this B should be negative.
That's right, it is. Yes, so this is the binding, that's the saturation, and here's the Coulomb repulsion. Okay? And there's no shape. This is spherically symmetric. Okay? So that's our simple model. And then we just dump a bunch of nucleons into a box and see what shape they like. Okay, and here are some still frames from a movie I'm going to show you in a second. Let's start at high density where the matter is uniform. This whitish, the light color is high density. The brown is a lower density surface. Okay? So you start with uniform matter. As you decrease the density, you want to stay nuclear matter density, and that means that you have little voids. And those voids can't grow too big because of Coulomb. So you get this Swiss cheese phase. And in fact, the holes can be a nice Coulomb lattice. And we can call that anti-Noki if you like, where Noki is roundish.
And this is athermal. There's no entropy in this, or is there?
Actually, this simulation is semi-classical. We use a fake temperature to simulate a little bit the quantum zero point motion. Okay, and if you go down in density, you get these tubes. So you have these low density holes in high density matter. So this is anti-spaghetti. Here's lasagna. You have flat plates, and thankfully anti-lasagna is the same thing as lasagna. And then the flat plates break up into cylinders, so spaghetti. And if you look in the slide, the spaghetti is actually arranged in a hexagonal lattice. Okay.
One scale.
So this is a couple hundred Fermis. So the features are a little bigger than a nucleus.
In the simulation, the features are fixed by your parameter lambda, screening parameter.
The screening is actually not so important. It's the balance between Coulomb and nuclear attraction.
But they are both in lambda in your one
So-
lambda
so-
and two lambda.
The Coulomb depends on E squared and some length scale,
I understand.
and the nuclear depends on these guys, and that's the balance. The lambda is a small perturbation to this.
So the scale of this pasta is not set by lambda.
No, that's right.
It's not-
The periodic table ends at 92-ish because of the balance between nuclear attraction and Coulomb repulsion. So that's the size of a nucleus or the size of a piece of pasta. Okay, so the movie is to start at high density. It's a simpler initial condition.
So, sorry, and you don't have no nuclei, right? It's just protons and neutrons.
That's right. So this is molecular dynamics in the nucleon coordinate.
And that thing is the nuclei which form.
That's right.
Okay, great.
Okay, and we'll start at high density. We put the nucleons in uniformly and let them choose the shape, and then we slowly expand the box. So as the box expands, the density goes down. Okay, and let me emphasize, Andre Schneider is the one who did these beautiful graphics and did the simulations. Okay, so thermal fluctuations, you have the Swiss cheese voids forming, and they percolate, and soon it's going to turn into lasagna. So lasagna, you get these sheets, and now the lasagna is going to break up into spaghetti. So it's starting to break up. So if you look at the side, you see the spaghetti, and if you're quick, you can see that's a hexagonal lattice. So look there. And then the spaghetti is going to fission into a bunch of gnocchi, a bunch of individual meatballs, which are nuclei.
The hexagonal lattice is stabilized by the Coulomb repulsion?
Yes. So two-dimension hexagonal lattice. And now, if you go a little lower, we'll have a body-centered cubic crystal lattice of more or less round nuclei.
When I and a graduate student did this sort of thing in continuum version, what was important was the surface energy, to the nuclear surface energy to the Coulomb energy. What surface energy does your sum of Gaussians give you?
Yes, so we fit the binding energy of uniform nuclear matter.
That's the volume energy.
And so if you did what's called a leptodermis expansion, and you can determine the surface energy coefficient, it's not dead on, but it's not crazy.
So it's close.
Yeah.
YP the proton fraction.
Yes.
What, and why does that say constant?
Oh, so in certain situations, if the dynamics is fast, there might not be enough time for weak interactions to optimize, change the neutron to proton ratio. For simplicity, we just kept it constant. And in fact, this value is somewhat artificially high. In a neutron star, it's much lower. But this just helps with make it easier to simulate. Okay, gosh. How can you smelt the nuclear pasta? So your question again, is any of this real? We want to find observable sensitive to the complex shapes. One fun thing to start with is in a supernova, you radiate tremendous numbers of neutrinos. Some of the neutrinos can have wavelengths comparable to the pasta. So you can actually have coherent neutrino pasta scattering. That scattering is described by the static structure factor. So it's this density-density correlation function. The neutrinos actually scatter from neutrons. So this is the static structure factor of the neutrons. And so we determine that from the molecular dynamics simulation. Alternatively, electron pasta scattering, it's the same static structure factor, except it's the protons you're scattering from the charge. And the electron mean free path gives the shear viscosity, the thermal conductivity, and the electrical conductivity. Okay, so the nuclear pasta depends on electron pasta scattering. And then coming back to changes in YE, the electron fraction or the proton fraction, you could also have hysteresis. If I expand the box too fast, then the shapes don't keep up, and you can have bulk viscosity. And that bulk viscosity can be important for the damping of some neutron star oscillation modes. And in particular, these so-called R modes, which may be important when neutron stars rotate fast. And those modes could be made stable if there's enough bulk viscosity from the pasta. And you could think about the shear modulus, and you might want to average over some orientations. The shear modulus of the pasta can be important for some neutron star oscillation. Okay?
And these oscillations are observed again in gravitational waves, or?
Maybe, not yet. We're looking for them. There are claims.
The hope is to observe them in gravitational waves.
Yes. And maybe even in gamma ray bursts. Okay, so conductivity of the pasta. Let me try and get a little bit in here, and maybe we'll be able to say a few things before I quit. So Pons et al. Have speculated that an impure pasta layer could have a low electrical conductivity, and this might lead to the decay of magnetic fields. So the strong magnetic field of some neutron stars can be supported by currents deep in the crust where the pasta is. And if somehow the pasta was impure and had a low conductivity, then the magnetic field could decay away in say, 1 million years. And that might explain why no isolated X-ray pulsars are observed with rotation periods longer than 20 seconds. So the magnetic field slows down the rotation rate of a neutron star, and after a long time, the magnetic field goes away. Then the star stops slowing down, and it just stays. We have no longer periods than that. Okay, so he was talking about the electrical conductivity, but the electrical conductivity and thermal conductivity are closely related. It's the same electrons. And so let's go back to what I showed near the beginning about the crust cooling light curves. So do you have some disordered state in the pasta? And this is one of the simulations with 200,000 nucleons. We start it from uniform distribution, and the nucleons quickly form the layers, but they have these topological defects, these ramps connecting the different layers. If we bias the simulation with just a very small potential that we leave on just for a beginning little bit at the start, we can get nice, clear, clean layers, and these layers should have no connections like this between them. And then if you calculate the static structure factor for electron pasta scattering, this is a function of momentum transfer, and this is the angle with respect to the normal to the lasagna plane. If there are no defects, the red is a big static structure factor, so the static structure factor is small, and with those topological defects, you get more scattering, and so this has a lower electrical and thermal conductivity than if the defects were not there. Okay, and now we can come back. So this is the temperature of the surface of the star versus days since accretion stopped, and this is a log scale, so pay attention. This is some data. This is a different star, but it's very like the star I showed you before. the late time is when you're sensitive to the thermal conductivity of the pasta. And so actually there's one data point here. Suggestive, it's a start. This is where you can look for the thermal conductivity of the pasta. So 10 years-ish, 5 to 10 years after accretion stopped, that's when the thermal wave from the pasta depth would reach the surface. Okay, so that at least is a place to look.
But there are no observation points there yet, or there is one?
So there's one point.
Or you claim it has been detected?
No. I admit there's one point.
But it's a direct.
So this is a start. I'm saying this is a place to look, and here's one data point. You can look in other stars. Some stars don't make it easy for you. For example, you have another episode of accretion before it cools this long. That's just trying to find an observable that's related to the defects in the pasta.
So you are saying that there is a hope that along these lines, eventually there will be some,
Yes.
either confirmation or other way around.
Okay, and gosh, we're going badly over time, so I'm going to try and do I get like 2 or 3 minutes?
Sure.
What the defects look like, this is, the story takes a strange turn. Greg Huber is a biophysicist. At the time, he was deputy director of the Institute for Theoretical Physics in Santa Barbara. And he came to us and said, your defects in pasta look exactly like the structures we've been seeing in biophysical systems, and in particular, the endoplasmic reticulum ramps that were observed in salivary gland cells of mice. Okay, so at least I've explained why I have a silly mouse in the picture.
Can you explain the explanation? Or it should be fruitless, okay, yeah.
So let me at least show it to you, and then probably not, but I'll try. So 2 seconds, here's the cell nucleus. This thing is the endoplasmic, and the structure of this, and it has flat sheets that look like pasta, so that's a good start. And now, this is way outside of my expertise. The biologists slice the biological sample ultra thin. The slices collect on a tape. You make 2-dimensional electron micrographs of the slices, and then you put the stacks back together on a computer, and that's this picture. So this is a 3-dimensional electron micrograph of the endoplasmic reticulum, a small sample of it, in a mouse. So this is 1 gram.
What is sorry, you keep repeating endoplasmic reticulum as if it makes any sense.
Red color. This thing here.
It's an organelle within a biological cell.
Yes.
It does useful things.
You die without it.
So there, you have flat surfaces, and there are machines on the flat surfaces that make proteins. Okay. And the question is, how are these flat sheets supported, and maybe these ramps hold them together. Okay. So this is biology at 1 gram per cubic centimeter. This is our molecular dynamics simulation at 10 to the 14 grams per cubic centimeter. So there's a helicity to these ramps. If you curl your fingers, the cars driving along these parking garage levels, the thumb points in the direction that you go on. So this is a right-handed, and there's a left-handed where it curls in the other direction to go down. Okay. Great. And the biologists have gone further, and they say, well, let's think of writing the energy of the system as an integral over the Gaussian curvature. You have some surface, there's a curvature in one direction and in the perpendicular direction. A saddle is when you have the one positive curvature and the other negative curvature, and that actually gives an attractive energy here. So if C1 and C2 have the opposite sign, then that's attractive. And so they describe these ramps that way, and they predict that one ramp will interact with another ramp, and you can form, for example, a dipole wall where you have a wall of right-handed down here and a wall of left-handed up there. And this is one of our molecular dynamics simulations, which actually both of these are our molecular dynamics simulation, that has a dipole wall. So there's a total of 8 ramps, 4 right-handed and 4 left-handed, and they're arranged as a dipole. All the left-handeds are up and all the right-handeds are down. And the biologists say that the connections are at 90 degrees with respect to the levels. For dipoles, if you have quadrupole, then they should be at 45-degree angle. And here's a pattern where you have left, right, so there's quadrupole. And I actually printed out an example. So this is our molecular dynamics simulation. There's about 75,000 nucleons in a box, and we just print out one density contour, and there's 4, 2 left and 2 right-handed ramps. What does it mean that these have the same shapes? The short answer is I don't fully know, and I apologize. I want to say the energy of some systems can depend on the geometry in universal ways. Nevertheless, what I can say is there's a long history to this. Nuclear fission, nuclear fusion, indeed nuclear pasta, the very names, atomic nucleus, and nuclear physics, the field of science I work in, these are all analogies with biology. So there's a long history to this. Okay? And after that, and rattling on way too long, I thank you very much for your attention, and let me just emphasize my excellent collaborators. A lot of this work was done with Matt Kaplan. Together we wrote this RevMod article. Greg Huber is the biophysicist, and Alex Deibel. So gosh, thank you very much. I really appreciate it.
Thank you, Chuck. Question.
Yes. So you showed the simulation with the body-centered cube, said it works well. We know that Landau's theory indeed predicts that there would be a body-centered cube. But what happens if I put a face-centered cube?
Very small differences. So
you don't know really what the crystalline structure is.
That's right. We think it's body-centered. If it's face-centered, observationally you can't tell. But we can say that it's relatively clean. So even if it's face-centered, it can have lots of impurities.
Any other questions? Well, we had a lot of questions in the course of the talk, so that's probably why it's exhausted. Okay, so if there are no questions, let's thank Chuck again for his interesting talk.